Somewhere in the constellation Cygnus, a star roughly 20 times the mass of our Sun is committing a slow, spectacular act of destroying itself. Every second, it flings an ocean the size of Earth into space, not in a single explosion, but in a continuous, screaming wind that peels its own atmosphere off layer by layer. What's left behind is something no ordinary star ever shows the universe. Its own naked, thermonuclear heart glowing hotter than 100,000 degrees, fusing helium and carbon in plain view. These are the Wolf-Rayet stars, cosmic strippers stripping themselves. And what they leave behind when they finally give up is not a whimper, not even a regular supernova. It's one of the most violent deaths the cosmos allows, and it may be the birth cry of a black hole. Tonight, we go inside that final rage. Before we go any further, if this kind of deep space exploration is something you enjoy, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. There is a star in the constellation Sagitta, small and easy to miss with the naked eye, called WR124. To ordinary photographs, it looks like nothing special. Just another point of light against a black background, but if you turn a good telescope on it and look carefully, you will see something extraordinary. The star is not alone. It is sitting inside a bubble. A great glowing shell of hot gas, about 6 light years across, surrounds it in every direction, blown outward and lit up from the inside. A lopsided balloon of luminous matter that was not there a few thousand years ago, and did not come from anywhere else. It came from the star. Every part of that glowing shell used to be a piece of WR124 itself. Layers of the star that were flung off into space by a wind so violent that it stripped the star bare while we were still learning to build telescopes. This is what a Wolf-Rayet star looks like when it is caught in the act. Not dying quietly, not blazing steadily like our Sun, but tearing itself apart in the open at speeds of thousands of kilometers per second, in a process that is not a single explosion, but a continuous, screaming, uninterrupted eruption that goes on for hundreds of thousands of years. The WR124 is roughly 20 times the mass of the Sun. It is around 15 times the size of the Sun. Its surface, if you can even call it a surface, sits at a temperature of about 44,000 Kelvin, hot enough that most of what it emits is not visible light, but harsh ultraviolet radiation. And its wind carries away roughly 1/100,000th of a solar mass every year. That does not sound like much until you do the math. Continue that for 1,000,000 years, and you have thrown away an entire sun of material. The star has been doing this for a long time. Long enough that the shell of ejected gas surrounding it, catalogued as M1-67, has expanded to roughly 3 to 6 light years across, and is still expanding. That shell is not smooth. It is knotted, filamented, full of dense clumps and empty pockets, because the wind is not perfectly steady. It surges, it hesitates, it collides with material thrown off earlier. Some of those knots and filaments are the size of small solar systems, and every one of them was once part of the star. If you took a movie of the surrounding nebula on a timescale of tens of thousands of years, you would see it churning like a slow, unnaturally illuminated storm. And in the center of it all sits this compact, blindingly hot, bluish-white object, quietly emptying itself into the vacuum. Now here is the strange part. The star does not look emptied. It still glows fiercely. In fact, if you measured its luminosity, it would come out at about 500,000 times the luminosity of the sun. This is not a dying candle. It is a floodlight. A beacon that would burn out your retina if you stood anywhere near it. Nothing about its brightness suggests it is running out of material. Nothing about its colour suggests it is fading. And yet, at the same time, it is bleeding. It is losing its outer skin at a rate that makes ordinary stars look inert. Somewhere buried underneath all that luminosity is a core doing something so violent, so energetically extreme, that it is pushing its own atmosphere clean off itself into deep space forever. That is a Wolf-Rayet star, and WR124 is only one example. There are others just like it scattered across the Milky Way, each one a monster caught mid-strip, each one revealing something no ordinary star ever lets you see, its own interior laid bare to the vacuum. WR124 is not even the closest bright example. If you happen to live in the southern hemisphere and you go outside on a clear night and look up at the constellation Vela, you can see, with your naked eye, a bright blue point of light called Gamma Velorum. It looks like a perfectly ordinary hot star, one of many in that patch of the southern sky. It is, in fact, one of the brightest Wolf-Rayet stars we know of. From the outside, it looks like nothing unusual, but turn a spectroscope on it, and its light comes apart into that same peculiar signature that has puzzled astronomers since the middle of the 1800s. There is a Wolf-Rayet star hiding in plain sight in the naked eye sky, and most of the people who have looked up at it over the centuries had no idea what they were looking at. To understand why any of this is so extraordinary, you have to understand what an ordinary massive star looks like. A normal star, like our sun, is a stable object. It has a core where hydrogen is being fused into helium, and a series of layers stretching outward above the core, each one cooler and less dense than the one below. The outermost layer, the one you actually see when you look at the sun, is called the photosphere. That is the layer whose light escapes into space. Above the photosphere, there is a thin, hot, structured atmosphere. Below the photosphere, everything is opaque. You cannot see into the sun. You cannot see any of the interior structure. The photosphere is a curtain, and behind it, the real business of a star happens in the dark. This is true of almost every star you have ever looked at. When you observe a star, you're looking at its outer skin, not its interior. What is going on in the core, where the fusion happens, is hidden from you by billions of kilometers of overlying gas. That gas has to be there. It provides the pressure that keeps the core stable. It provides the environment in which fusion happens at just the right rate. Without an envelope, a star cannot be a star in the normal sense of the word. It is just a naked ball of nuclear fire. A Wolf-Rayet star is essentially that. A star whose envelope has been ripped away. A star whose curtain has been shredded. When you look at a Wolf-Rayet star, you are not looking at a normal photosphere. You are looking at what was, until recently, deep interior material. The layers you are seeing were once buried under a hydrogen envelope tens of solar masses thick. That envelope is gone, blown off, scattered into the surrounding interstellar medium at speeds of thousands of kilometers per second. And what is now exposed to the vacuum is the fusing region itself, or almost the fusing region. In some cases, you're looking directly at the ashes of hydrogen burning. In others, you're looking at the ashes of helium burning. You're seeing, without any protective atmosphere in the way, what a stellar interior actually looks like. This is not something an ordinary star does. This is not even something most massive stars do. To reach this state, a star has to be enormous, luminous, and unstable enough to have essentially disassembled itself from the outside in. It takes a very particular combination of physics to produce this outcome, and only the most massive stars in the galaxy ever get there. Almost every Wolf-Rayet star started life with somewhere between 20 and 80 solar masses, sitting near the very top of the stellar mass function, in a category so rare that only a fraction of a percent of all stars are ever going to become one. Which raises an obvious question. If they are so rare, and if they are so extreme, how did we ever find them in the first place? How did anyone know they existed? The answer takes us back to Paris in the year 1867, to a young science that was still figuring out what stars were made of. At that moment in history, astronomy was in the middle of a revolution. For thousands of years, astronomers had looked at stars and could tell you where they were, how bright they were, and roughly what color they were. That was it. What stars were actually made of, what they were doing, why they shone at all, none of that was known. Stars were points of light. Then, in the middle of the 1800s, a new tool changed everything. The tool was the spectroscope. A spectroscope takes the light coming from an object and spreads it out by wavelength, the way a prism spreads sunlight into a rainbow. When you do this to starlight, something remarkable happens. Instead of a smooth rainbow, you see a rainbow crossed with a set of dark lines. Very specific, very sharp, very reproducible dark lines. Those lines are called absorption lines, and they are a fingerprint of what the star's atmosphere is made of. Every chemical element has its own unique set of lines. Hydrogen has one pattern, iron has another, calcium has another. If you know how to read the pattern, you can look at a distant star and tell what elements are in its atmosphere without ever leaving Earth. This was a stunning realization. It meant for the first time that astronomers could do chemistry on stars. They could tell you what a star was made of just by catching a little bit of its light and running it through a spectroscope. In the decade before 1867, an Italian astronomer named Angelo Secchi had started using this technique to classify stars by the pattern of their absorption lines. He grouped them into families based on the character of those dark lines, laying the foundation for the stellar classification system that astronomers still use in modified form today. And then, in the summer of 1867, two astronomers at the Paris Observatory found something that did not fit. Their names were Charles Wolf and Georges Rayet. They were both trained observers, both experienced with the new spectroscopic techniques, and they were systematically sweeping through the sky, taking spectra of stars and looking for interesting objects. On a particular evening, they turned their instrument toward the constellation Cygnus and pointed it at three stars that, in ordinary photographs, looked completely unremarkable. Modest brightness, nothing that would catch your eye if you were just looking up. The stars are now known as HD 191765, HD 192103, and HD 192641. But at that moment, they were just 3 points of light in a rich patch of the northern sky. When Wolf and Rayet looked at their spectra, though, what they saw was not the pattern anyone expected. The stars did not show a smooth rainbow crossed with dark absorption lines. They showed a rainbow crossed with wide, glowing, bright emission lines. Not dark lines subtracted from the light, but bright lines added on top of the light. Emission features so strong that they dominated the spectrum, so wide that they looked less like sharp fingerprints and more like fat glowing bands smeared across the color of the star. This was unheard of. Stars did not do this. Every other star Wolf and Rayet had ever looked at, and every other star that had been catalogued spectroscopically up to that point, showed absorption lines, dark against a bright background. Their 3 stars in Cygnus showed the opposite, bright emission lines against the continuous glow of the star. Something was fundamentally different about these objects. Something in the physics of their atmospheres was operating in a completely different mode. Wolf and Rayet published their finding, and it caused a stir. Astronomers around the world tried to explain what was going on. Some suggested that the stars were surrounded by unusual clouds of gas. Others thought the atmospheres were shockingly hot. A few wondered if these might be an entirely new class of object. But without a physical theory of stars, without knowing what the interior of a star was actually doing, there was no way to make sense of what Wolf and Rayet had seen. For decades, the objects were treated as astrophysical curiosities, a peculiar group, a footnote, something odd in the sky that would eventually be explained once the science caught up. The name stuck, though. In their honor, the class of star came to be called Wolf-Rayet stars, and over the following century, as more and more of them were catalogued, as their spectra were measured with better and better instruments, it slowly became clear what those bright emission lines were actually telling us. Here is the physics, in the simplest possible terms. Think about how a normal star produces its spectrum. Deep inside the star, in the hot core, light is produced by the various reactions and thermal processes going on there. That light travels outward through the star, absorbed and released again by countless atoms along the way, until it finally reaches the photosphere and escapes into space. Just above the photosphere is a slightly cooler atmosphere, and as the light passes through it, atoms in that atmosphere absorb specific wavelengths, the wavelengths that correspond to their internal energy transitions. When astronomers on Earth catch that light and spread it out, they see a bright, continuous rainbow with narrow dark gaps at exactly those absorbed wavelengths. Those dark gaps are the absorption lines. They tell you what is in the star's atmosphere. Now imagine that instead of a thin, quiet atmosphere sitting just above the photosphere, you have a huge extended atmosphere in violent outflow. The wind coming off the star is enormous, dense, and fast. As light from the star tries to pass through it, some of it does get absorbed, the same as before. But the outflowing gas is also being heated and excited by the same intense radiation. And when atoms in that gas are excited and then relax to lower energy states, they emit light at their own characteristic wavelengths. If there is enough of this outflowing, glowing gas, the emission from it can overwhelm the absorption. Instead of narrow, dark lines cut into the spectrum, you get broad, bright lines added on top. The wide shape of the lines is a signature of the speed of the outflow. Different parts of the wind, moving at different velocities toward and away from us, emit at slightly different wavelengths shifted by the Doppler effect, smearing what would have been a narrow line into a broad glowing band. From the width of that band alone, you can measure how fast the wind is blowing. So a star with fat, bright emission lines in its spectrum is not just a peculiar object. It is a star whose atmosphere is in extraordinary bulk motion. The light you are catching is not from a placid, static photosphere. It is from an atmosphere blowing itself outward at thousands of kilometers per second. So vast and so radiant that it is doing the light show all on its own. Wolf and Rayet, when they saw those emission lines in 1867, were looking at the signature of a stellar wind that would not be understood in detail for another 100 years. They had accidentally stumbled on evidence of the most extreme mass loss in the stellar zoo. Once astronomers realized this, they started counting Wolf-Rayet stars and finding out how many of them the galaxy contained. The results were surprising. Even now, after more than a century and a half of searching with progressively better instruments, only about 667 Wolf-Rayet stars have been catalogued in the entire Milky Way, and probably a few thousand more are hidden behind dust or too dim to catch. That is a tiny population. The Milky Way contains somewhere between 100 and 400 billion stars. If you assume even the highest estimate for the true number of Wolf-Rayet stars, they still represent something like 1 in every 10 to 50 million stars. They are effectively a rounding error in the census of the galaxy. And yet, individually, each one is a monster. Every Wolf-Rayet star is descended from a star that started life with at least 20 times the mass of the Sun. Most of them come from progenitors of 30, 40, 60 solar masses. The very rarest kinds, at the top of the population, may have started life at 80 solar masses or more. These are stars from the extreme upper end of the mass distribution. Stars that live fast and die young and are, at every stage of their lives, straining against the physical limits of what a ball of gas holding itself together by gravity can actually hold. The reason they are so rare, in other words, is not that there is anything unusual about becoming a Wolf-Rayet star once you have the right ingredients. The reason they are rare is that the ingredients themselves are rare. You need a truly massive star to begin with. Massive stars are uncommon to start with, because the process of forming stars turns most of its gas into small, low-mass stars, red dwarfs, orange dwarfs, sun-like stars, and only occasionally, in the right conditions, makes a monster. And even then, that monster has to survive long enough, in the right kind of environment, to reach the Wolf-Rayet stage before something else happens to it. Because for a massive star, several things can happen. It can explode as a supernova relatively early. It can lose mass through less extreme processes, and end up as a blue supergiant or red supergiant instead. It can be a member of a binary system in which its companion strips away its envelope for it. The Wolf-Rayet outcome is only one of several possible endings, and it requires a very particular kind of history. Which brings us to the last thing to sort out in this opening picture: how a Wolf-Rayet star is different from the other massive stars in the sky. Because on the surface, there are a lot of massive stars that look impressive and lose a lot of mass. And it is fair to ask what makes Wolf-Rayet stars a distinct category. The answer is subtle, but important. An ordinary O-type star is a very hot, very massive, very luminous main sequence star. It is fusing hydrogen in its core, just like the Sun does, but at a monstrously accelerated rate. O-type stars have strong winds. They lose mass, but their mass loss is modest compared to a Wolf-Rayet star, and crucially their envelopes are still fully in place. The hydrogen skin is intact. You're still looking at a normal photosphere. A blue hypergiant is a step further along. It is a very luminous, evolved massive star that has begun the process of losing its envelope in earnest. The winds are strong, the mass loss is significant, but the star is still in the middle of shedding its outer layers. It has not yet been stripped down to interior material. If you look at its spectrum, you see complicated features that reflect an envelope in disarray, but you do not yet see the naked ashes of nuclear burning. A luminous blue variable is an even more unstable object. Stars like Eta Carinae, whose great eruption in the 1840s briefly made it one of the brightest stars in the southern sky, fall into this category. Luminous blue variables have episodes of enormous mass loss, sometimes shedding several solar masses in a single outburst. But they are erratic, unpredictable, and often stuck in a kind of dance between different states of instability. Many astronomers think that some luminous blue variables are the immediate predecessors of Wolf-Rayet stars, that when they finally lose enough mass, they will settle into the Wolf-Rayet state, but they themselves are not there yet. A Wolf-Rayet star is what happens after all of this. It is the endpoint of the stripping process, or nearly so. The envelope is essentially gone. The star is not shedding its hydrogen skin anymore. That skin is already blown away. What remains is a compact, hot, luminous object whose surface is made of what used to be interior material. The wind is not tearing off an envelope. The wind is now attacking the exposed layers of the fusion factory itself, going deeper into the star with each passing millennium, which is what makes it such an extraordinary object to look at. Every other kind of massive star still hides its interior. Wolf-Rayet stars have thrown that hiding place away. They are the only stars in the sky that let you look in real time at the fusing heart of a massive star as it burns. And every one of them is doing this to itself. Not because a companion stole its envelope, not because a random cosmic event tore off its skin, but because its own light, its own radiation, pouring out of that ferocious core, is powerful enough to blow its own atmosphere off into space. The star is committing this act on itself, with its own energy, using its own light as the weapon, which is a very strange and very specific piece of physics, and it deserves a very careful look. Because it is not obvious how radiation, which we normally think of as weightless and gentle, the same stuff coming out of a bedside lamp, the same stuff warming your skin at the beach, could ever be violent enough to strip a star. But it can. It can be violent enough not just to strip a star, but to strip the most massive stars in the universe, the ones with the strongest gravity, the ones with the deepest gravitational wells to escape from. And once you understand how that happens, you understand why Wolf-Rayet stars exist at all, and why they occupy this strange, brief, luminous phase between an ordinary massive star and the violent way in which it will end. There is something deeply counterintuitive about the idea that light can move things. In everyday life, light is the most immaterial thing you can imagine. You can walk through a beam of it without noticing. You can stand in bright sunshine and feel warmth on your skin, but you do not feel yourself being pushed backward. A camera flash going off in your face is dazzling, but it does not knock you over. Every intuition we have from ordinary human experience says that light is weightless, momentumless, gentle, something that carries information and heat, but not force. That intuition is wrong. Light does carry momentum. Every single photon, every particle of light, is a tiny bullet with a tiny amount of push built into it. The push per photon is astonishingly small. So small that under normal circumstances we cannot detect it without extraordinarily sensitive equipment. But it is real. And in the right conditions, when you have enough photons streaming out of a hot enough source, the collective push of all those tiny bullets adds up to a force that can move mountains. It can rip the outer layers off a star and hurl them into interstellar space at thousands of kilometers per second. It can do this for hundreds of thousands of years without pause. And the only reason we did not figure this out until modern physics came along is that the sun, which is our reference point for what a star is nowhere near powerful enough to do it to itself. To understand what a Wolf-Rayet star is doing to itself, you have to understand this, because everything about the Wolf-Rayet phenomenon flows from a single physical fact. Light pushes, and when light pushes hard enough, matter has no choice but to move. Start with a single photon. When a photon leaves the surface of a hot object and travels outward, it carries a small amount of momentum. If that photon hits a particle of matter and gets absorbed, all of that momentum transfers to the particle. The particle recoils in the direction the photon was originally traveling. If the particle then re-emits the photon in some random direction, the outgoing photon carries some of that momentum away again, but not necessarily in the same direction it came in. On average, absorbing and re-emitting a photon nudges the particle slightly outward, away from the source of the photon. Now stop looking at one photon and one particle and start looking at trillions upon trillions of them. Imagine a hot star pouring photons outward from its surface in every direction, and imagine a shell of gas sitting above that surface. Every photon that hits that gas has a chance of being absorbed. Every absorption transfers a tiny outward kick to the atoms in the gas. Multiply the tiny kick per photon by the enormous number of photons streaming outward every second, and you get a force. A steady, relentless outward force acting on every gram of gas above the surface of the star. This force is called radiation pressure. It is one of the most important forces in stellar astrophysics, and for a star like the Sun, it is a small correction. For a Wolf-Rayet star, it is the dominant force determining how the star behaves. For the Sun, radiation pressure is roughly negligible in the outer layers. The Sun's outer atmosphere is held down mostly by gravity, and gravity wins easily. A tiny bit of material escapes as the solar wind, about 100 trillionth of a solar mass every year. That is such a small number that if the Sun kept losing mass at that rate for its entire lifetime of 10 billion years, it would only have lost about 1/10,000th of its total mass by the end. The solar wind is real, but by any stellar standard it is a mere leak, not a torrent. It exists because the Sun's outer atmosphere, the corona, is heated to millions of Kelvin, hot enough that thermal pressure alone flings a small fraction of particles outward into space. Gravity is winning. Now, change the star. Instead of the Sun, consider a star with 30 solar masses. That star is not just 30 times more luminous than the Sun, it is far more luminous than that. The relationship between mass and luminosity for main sequence stars is steep. Roughly, luminosity scales as mass to the 4th power for very massive stars, which means a 30 solar mass star is not 30 times brighter than the Sun, but somewhere around 100,000 times brighter. And when we get to a star that is currently in the Wolf-Rayet stage, coming down from a starting mass of 40 or 50 solar masses, its luminosity can easily reach 500,000 to 1,000,000 times the Sun's luminosity. Some of the most luminous Wolf-Rayet stars in the galaxy hit 2 million times the luminosity of the Sun. At those luminosities, radiation pressure is no longer a small correction. It becomes comparable to gravity itself, and when radiation pressure gets comparable to gravity, everything changes about how the star behaves. There is a specific luminosity at which a radiation pressure exactly balances the gravitational force pulling matter inward. This limit is called the Eddington luminosity, after the British astrophysicist Arthur Eddington, who worked out the physics of it in the early 1900s. The Eddington luminosity depends on the mass of the star. A more massive star has a higher Eddington luminosity because it has stronger gravity holding onto its outer layers. But it is a specific number, and it sets a hard ceiling on how luminous a star can be while still holding itself together in a stable state. If a star's luminosity ever exceeds the Eddington limit, radiation pressure wins. The outer layers cannot be held down anymore. They get pushed off. For a 30 solar mass star, the Eddington luminosity works out to about 1 million times the luminosity of the Sun. For a 50 solar mass star, it is closer to 1.5 million. For an 80 solar mass star, it is around 2.5 million. Now compare those numbers to the actual luminosities of massive stars. A very luminous Wolf-Rayet star can radiate at around 1 million times the luminosity of the Sun, which puts it right at the doorstep of the Eddington limit for a mass of around 30 solar masses. If the star's actual mass has dropped below that as a result of losing its outer layers, then it may already be sitting above its own Eddington limit locally, in specific layers of its atmosphere. That is a star that cannot be stable. That is a star that is telling you, through the sheer intensity of its light, that it does not have the gravitational grip to keep its outer material in place. Every Wolf-Rayet star lives near this edge. Every one of them is a star whose brightness is straining against its own gravity. And when they lose enough mass, when the ratio of luminosity to mass gets high enough, the outer layers cannot resist. They get pushed outward. They join the wind. They leave the star and go into space. But there is a subtlety here that is worth spending some time on, because it is the key to understanding why Wolf-Rayet winds are so extraordinary. Radiation pressure alone, in a general featureless sense, is not actually strong enough to do what a Wolf-Rayet wind does. The Eddington argument tells you that when total radiation pressure equals total gravity, something breaks. But in the atmospheres of these stars, the real physics is more selective than that. Radiation pressure acts most powerfully on gas that is very good at absorbing photons of the specific wavelengths the star emits. And the way you get gas that is very good at absorbing specific wavelengths is by putting metal atoms in it, not metal in the everyday sense. In astrophysics, a metal is any element heavier than helium. Carbon is a metal, nitrogen is a metal, oxygen is a metal, iron is a metal, and iron in particular is very important. These heavy elements, when they exist as ions in a hot gas, have complicated electronic structures. Each ion has hundreds or thousands of possible transitions between energy states, and each transition corresponds to a specific wavelength of light that the ion can absorb. When a photon of exactly the right wavelength comes streaming out from below and hits that ion, it gets absorbed. Momentum transfers, the ion gets pushed outward, then the ion re-emits, drifts slightly, absorbs another photon of a different wavelength, gets pushed again, and so on. The absorption spectrum of a metal ion is essentially a comb of thousands of narrow features that let it catch photons across a wide range of the star's output. This mechanism, in which specific spectral lines of specific ions do the work of catching photons and transferring their momentum to the gas is what powers the winds of hot, massive stars. It is called a line-driven wind. The line refers to the spectral line of the ion, the sharp feature in the atomic spectrum where absorption happens. And the mechanism is enormously efficient because the metal ions are not just catching one wavelength or two. Iron alone, in the ionization states you find in the atmosphere of a hot star, has tens of thousands of possible absorption lines. Each line catches its own slice of the star's output. Add up all the lines from all the important metal ions, and you have a system that is exquisitely tuned to soak up the light coming from below and turn it into outward push. The theory of how all of this works in detail was not worked out until 1975, more than a century after Wolf and Rayet had first noticed the peculiar spectra. 3 astrophysicists, John Castor, David Abbott, and Richard Klein, published a paper that laid out the mathematics of line-driven winds from hot massive stars, showing exactly how the momentum transfer from photons to metal ions could sustain the enormous outflows that had been observed. Their work was a breakthrough. For the first time, the winds of hot massive stars stopped being a mysterious empirical phenomenon and became something that could be calculated from first principles. Every subsequent refinement of the theory sits on the foundation they built. The direct observational signature of these winds is worth describing, because it is one of the most elegant diagnostics in stellar spectroscopy. When you look at the ultraviolet spectrum of a hot, massive star with a strong wind, certain spectral lines have a very peculiar shape. The blue shifted side of the line, corresponding to material moving toward us on the near side of the star, shows deep absorption. The red shifted side, corresponding to material moving away on the far side, shows bright emission. Together they produce an asymmetric line profile that looks like a bright peak with a dark trough cut into its blue edge. The dark trough tells you the wind is moving toward you. The bright peak tells you the wind is spread around the star in all directions. And the width of the whole feature tells you exactly how fast the wind is blowing. You can read the terminal velocity of the wind straight off the spectrum, without any theoretical model in between. This is why Wolf-Rayet winds are so much more powerful than the solar wind. The sun is not luminous enough for radiation pressure to matter much, and its atmosphere is not composed the right way to catch photons efficiently even if it were. A Wolf-Rayet star has both. It is bright enough that even ordinary radiation pressure is straining against gravity, and its atmosphere is packed with ions whose spectral lines catch photons with astonishing efficiency. Together, these two effects push the outer layers of the star off with such force that they leave at speeds we do not see anywhere else in the steady stellar universe. How fast do they leave? The number is worth stating carefully. Wolf-Rayet winds achieve what is called a terminal velocity, the speed the wind reaches once it has climbed far enough from the star that further acceleration is negligible. Terminal velocities of Wolf-Rayet winds range from about 1,000 kilometers per second at the low end to roughly 5,000 kilometers per second at the high end. The most extreme cases are moving at close to 2% the speed of light. To put this in perspective, the solar wind, at Earth distance from the Sun, moves at about 400 kilometers per second. Wolf-Rayet winds are 5 to 12 times faster than that, and they are moving that fast in the immediate vicinity of the star, not out at astronomical unit distances. A Wolf-Rayet star sits at the center of a bubble of gas That is howling outward at velocities that would let it cross the entire orbit of Neptune in less than a year. Now put the speed together with the amount of material being moved, and you get the mass loss rate. A typical Wolf-Rayet star loses somewhere between 1/100,000th and 1/10,000th of a solar mass per year. That is roughly a factor of 100 million to 1 billion times higher than the solar mass loss rate. To make this concrete, imagine watching a Wolf-Rayet star continuously for 1 million years. Over that time, it would throw off between 10 and 100 solar masses of material. That is potentially more mass than a decently sized star has to begin with. In practice, of course, the wind cannot keep going forever, because eventually the star runs out of outer layers to shed. But the fact that the wind can, on paper, get rid of 100 solar masses in a million years tells you everything you need to know about how violent this process is. A single Wolf-Rayet star, over its brief lifetime, can transfer more mass into the interstellar medium than there is in the entire disk of a small dwarf galaxy's worth of ordinary stars combined. Where does all that mass go? It goes into the surrounding space, and it does not go quietly. When the wind slams into the interstellar medium, or into material that the same star ejected earlier in its life, it creates shocks. Those shocks heat the gas to millions of Kelvin. They form the glowing bubbles and shells that we can photograph around Wolf-Rayet stars like WR124. They inject enormous amounts of kinetic energy into the interstellar gas. Over the lifetime of a single Wolf-Rayet star, the wind pumps out something like 10 to the 49 or 10 to the 50th ergs of kinetic energy, which is comparable to the total energy released in a supernova explosion. The Wolf-Rayet phase is essentially a supernova in slow motion, spreading its energy over hundreds of thousands of years instead of releasing it all in a single instant. And it does this before the actual supernova happens, which brings us to the aspect of Wolf-Rayet winds that turns them into a runaway process. And this is where the story gets its most elegant twist. The wind does not just shed the outer layers and stop. The wind actively makes itself worse. Here is what happens. When a very massive star settles into a stable main sequence configuration, its structure is arranged with a hydrogen envelope on the outside and a core of hydrogen fusion products deep inside. The hydrogen envelope is enormous. It represents most of the star's mass, and it acts as a kind of buffer between the fierce interior and the outside universe. The star's luminosity is determined by what is happening in the core, but the surface temperature and appearance are determined by the outer envelope. As long as the envelope is intact, the star behaves like an ordinary massive main sequence star. Very hot, very bright, but recognizable. Now let the wind start operating. The line-driven wind blows off the outermost layers of the hydrogen envelope. As those layers depart, the layers underneath, which used to be a little deeper and a little hotter, get exposed. Once they are the new outer layers, they are the ones facing outward into the vacuum. And because they are hotter and denser and richer in ions that absorb photons efficiently, they catch the outgoing radiation even more effectively than the layers they replaced. The wind gets stronger, more mass gets stripped. The next layer below, which is even hotter and even more efficient at catching photons, becomes exposed. The wind gets stronger again. This is a positive feedback loop. The more the star strips itself, the more efficiently it can strip itself further. It is not the case that the wind slows down as the star loses mass. Quite the opposite. Once a massive star crosses a certain threshold and starts shedding its envelope in earnest, the wind tends to accelerate. It bites deeper. It exposes hotter, more ionized material. It catches more photons. It transfers more momentum. And it keeps doing this until the star has essentially peeled itself down to its core. There is a natural stopping point to this process, though it is not gentle. Once the outer layers have been stripped down past the hydrogen envelope, the exposed material is no longer normal stellar atmosphere. It is helium, freshly minted by fusion, plus the ashes of hydrogen burning. This is what a Wolf-Rayet star of the nitrogen sequence looks like on the outside. It is essentially a helium star with a wind. As the wind continues to eat into that helium layer, it eventually exposes the products of helium burning, which are carbon and oxygen. That is a Wolf-Rayet star of the carbon sequence. If the wind keeps going, eventually you can end up looking almost directly at the layers where oxygen burning is happening, which gives you the extremely rare Wolf-Rayet stars of the oxygen sequence. Every one of these transitions is driven by the wind. Every one of them exposes deeper, hotter, more processed material, and every one of them is a step further into the interior of what used to be a normal, massive star. The wind is not just a process that happens on the outside of the star. It is a process that reaches into the star and pulls its structure apart from the outside in. There is one more piece of physics to add before this picture is complete, and it is the piece that has profound implications for what happens in different parts of the universe. Line-driven winds depend on metals. They depend specifically on the presence of heavy elements in the star's atmosphere to catch the photons. If a star is made of nothing but hydrogen and helium, with essentially no heavier elements at all, then line-driven winds are much weaker. There are simply not enough absorption lines to catch the light. Radiation pressure still exists, but the specific mechanism that makes Wolf-Rayet wind so powerful is missing. This creates a strong dependence of the whole Wolf-Rayet phenomenon on what astronomers call metallicity, which is just the fraction of a star's material that is made of elements heavier than helium. In the modern Milky Way, in the general neighborhood of the Sun, metallicity is at its solar value. Stars form from gas that is around 2% metals by mass. That is enough to power the full line-driven wind mechanism, and that is why we see so many Wolf-Rayet stars in our part of the galaxy. But go to a small nearby dwarf galaxy like the Small Magellanic Cloud, which has metallicity around 1/5 of solar, and Wolf-Rayet winds become weaker. Go to the very early universe when the first stars were forming out of essentially pure hydrogen and helium left over from the Big Bang, and line-driven winds effectively shut down. The first generation of massive stars, the ones that formed within a few 100 million years of the Big Bang, could not strip themselves the way modern Wolf-Rayet stars do. Their atmospheres didn't have the metals to catch photons efficiently. As a result, those first massive stars retained much more of their initial mass. They collapse at the end of their lives while still gigantic, and they may have formed black holes considerably more massive than the ones we typically get from Wolf-Rayet progenitors today. This has real observational consequences. When we look at galaxies with lower metallicity, we see fewer Wolf-Rayet stars for a given number of massive stars. We see different mass loss rates. We see different types of supernovae as the endpoints. The whole ecosystem of massive star death depends on how much metal is in the gas the stars formed from. Because metallicity controls the wind, and the wind controls how much mass the star loses before it explodes. It is worth pausing on how remarkable this is. The chemistry of the interstellar medium, the fraction of iron and carbon and oxygen mixed into the primordial hydrogen, controls whether a star can strip itself, which controls whether a star ever becomes a Wolf-Rayet star, which controls what kind of supernova or what kind of black hole it leaves behind. A property that seems as far from the physics of stellar deaths as you can get. The mixture of elements the star was born with ends up being one of the master switches that decides how the star will die. Turn the metallicity down and you get a different universe of stellar corpses. Turn it up and you get ours. Radiation pressure, then, is not just what pushes the outer layers off a Wolf-Rayet star. It is the mechanism by which the entire late-life history of a massive star is written. It is what determines how much of the original mass survives to the moment of core collapse. It is what determines whether the surface you are seeing is hydrogen or helium or carbon. It is what carves the structure of the exposed core, layer by layer, by choosing which layer will be the new outermost one after enough material has been blown off. And here is the strange consequence of all of this. When you look at a Wolf-Rayet star, you are looking at a star being consumed by its own light. Every photon that is doing the pushing was made deep in the core. It climbed through the layers, absorbed and re-emitted countless times until it finally reached the atmosphere. There, in that thin outermost skin, it got caught by the spectral lines of a metal ion, delivered its momentum, and then departed for interstellar space as part of the outflow. The photon carried with it a small piece of the star's future. Multiply that small piece by the trillion photons that a Wolf-Rayet star emits every second, and you get a stellar wind carrying away the very layers that made the light possible. This is the engine. This is what makes a Wolf-Rayet star different from every other massive star in the sky. Not that it is bright, not that it is massive, not even that it has a strong wind. Though all those things are true. What makes a Wolf-Rayet star Wolf-Rayet is that its own radiation, the same radiation that lets it shine, is powerful enough, and its atmosphere is composed the right way that it can turn its light into a weapon against itself. It is a star that has figured out how to use its own energy to disassemble itself from the outside in. And once you understand that mechanism, the question that follows almost immediately is, what does that leave behind? What does the interior of a massive star, once you have stripped off all its protective outer layers, actually look like? Because from the outside, every Wolf-Rayet star tells a slightly different story. Some show the ashes of hydrogen burning. Some show the ashes of helium burning. Some show something even deeper. The spectrum you see is a fingerprint of exactly how much of the original star is left, and where the wind has eaten to. And when astronomers learned how to read that fingerprint, they discovered that Wolf-Rayet stars come in a family with a clear internal order. An order that turns out to be a direct archaeological record of the stripping process itself. Imagine peeling an onion in reverse, not slicing off the outer skin and finding another skin below, but taking an onion whose layers are being torn off one at a time by a violent wind, and looking at whichever layer happens to be exposed at the moment. If you catch it early, you see the outer skin. If you catch it later, you see a middle layer. If you catch it very late, you see the layer just outside the core. And crucially, the layer you see is made of different material at each stage, because the interior of the onion is not uniform. It has structure, it has chemistry. Each layer represents a different phase in the onion's history. Now replace the onion with a massive star and replace the outer skin with hydrogen, and replace the deeper layers with the byproducts of nuclear fusion. What you have is a Wolf-Rayet star. And the wonderful thing about Wolf-Rayet stars, the thing that makes them one of the most useful objects in stellar astrophysics, is that they wear their history on their sleeves. When you look at the spectrum of a Wolf-Rayet star, you are not just seeing that it has a wind. You are seeing exactly which layer of the original massive star the wind has eaten down to. The chemistry of the surface tells you the depth of the excavation. And because the interior of a massive star is arranged in a very specific, physically predictable order, the surface chemistry of a Wolf-Rayet star tells you, with almost forensic precision, how much of the original star has already been thrown away. To make sense of this, you have to first understand what the interior of a massive star actually looks like. Not in terms of density or temperature, but in terms of what elements are there and where. Because inside a massive star, the elements are not mixed. They are stratified. And the stratification is a direct consequence of the physics of nuclear fusion. Fusion is the process that powers stars. It is what happens when small atomic nuclei get squeezed together hard enough that they merge into a bigger nucleus, releasing energy in the process. In the core of the Sun, the reaction that dominates is proton-proton fusion, in which 4 hydrogen nuclei ultimately combine to make one helium nucleus. That reaction only happens efficiently at temperatures above about 10 million Kelvin, and the Sun's core sits at around 15 million Kelvin, well above that threshold. Above the core, the temperature drops off, and below about 10 million Kelvin, hydrogen fusion effectively stops. So the Sun has a core where fusion is happening, and an envelope where it is not, and the boundary between them is set by temperature. For a massive star, the same idea applies, but at every step the numbers are more extreme. A star with 30 solar masses has a core temperature not of 10 million Kelvin, but of 30 or 40 million Kelvin. At those temperatures, hydrogen fusion no longer proceeds primarily through the proton-proton chain. Instead, it proceeds through a different set of reactions called the CNO cycle. In the CNO cycle, hydrogen still gets fused into helium as the net result, but the reactions use carbon, nitrogen, and oxygen as catalysts. Those nuclei are not consumed by the reactions. They cycle through, get hit by protons, transform between one another temporarily, and eventually end up back where they started, having facilitated the merger of 4 protons into one helium nucleus. Now here is the interesting fact about the CNO cycle. It processes carbon, nitrogen, and oxygen through the cycle at different rates. Some of the intermediate reactions are fast and some are slow. When the cycle reaches steady state, the net effect is that most of the carbon in the star's core gets converted into nitrogen, and some of the oxygen gets converted into nitrogen as well. If you took a sample of the core of a massive star that had been fusing hydrogen through the CNO cycle for a while, you would find that the abundance of nitrogen has grown dramatically at the expense of carbon and oxygen. This is a chemical fingerprint. It is the signature of hydrogen burning under CNO cycle conditions, and it says, "This material has been through the CNO cycle." Above the core of the star, in the envelope, the CNO cycle is not happening. The temperature is not high enough, but that does not mean the envelope is chemically unrelated to the core. In a massive star, there are typically convective and mixing processes that bring some processed material up from the core boundary into overlying layers, and there are extended regions just above the core where the temperature is still high enough that some CNO cycling has been happening, if only in trace amounts. And when the star reaches the end of its main sequence life, when core hydrogen is exhausted and the core contracts and heats up further, hydrogen fusion moves outward to a shell around the core. That shell is now the site of CNO processing, and the shell sits at a specific depth in the star. So even before you get to helium burning, the interior of a massive star has structure. Deep down, in the core, hydrogen is being turned into helium via the CNO cycle. The material there is enriched in helium and enriched in nitrogen, and depleted in carbon and oxygen relative to the star's original composition. Above the core, in a thick intermediate layer, the material has been touched by CNO processing to a lesser extent, still enriched in helium and nitrogen, but less dramatically so. And above that, in the outer envelope, the material is essentially unchanged from what the star was born with. Mostly hydrogen with some helium, with the small original amount of carbon, nitrogen, oxygen, and heavier metals mixed in. Now, let the wind start operating. The wind blows off the outer envelope first. That is the top layer of the onion, the material that is essentially unchanged from what the star was born with. While the wind is chewing through that layer, an outside observer sees a hot, massive star with an ordinary hydrogen surface. It looks like a normal main sequence O-type star, or perhaps a blue supergiant if the star has evolved off the main sequence. But then, once the wind has stripped away that outer envelope and reached the layers where CNO processing has been going on, the surface chemistry of the star changes. Now the outermost visible layer is not ordinary hydrogen envelope material. It is CNO processed material, enriched in nitrogen, depleted in carbon and oxygen. The spectrum of the star changes accordingly. The bright emission lines that dominate a Wolf-Rayet spectrum are no longer just lines of hydrogen and helium. They are lines of nitrogen, ionized nitrogen, multiple times ionized nitrogen. Nitrogen atoms in high energy states, glowing brilliantly in the ultraviolet and optical parts of the spectrum, revealing what the surface of the star is now made of. This is a Wolf-Rayet star of the nitrogen sequence. In the classification system, it is called a WN star. And when astronomers see a spectrum dominated by strong nitrogen emission lines, they know exactly what they are looking at. They are looking at a massive star whose wind has stripped off the original hydrogen envelope and has now exposed the ashes of the CNO cycle. The observation of nitrogen lines is a direct probe of the interior of the star. It is a diagnosis. It says, this star has been processing hydrogen through the CNO cycle, and enough of the outer material has been removed that we are now looking at the CNO cycle's chemical residue. The WN classification is not a single category. It has subtypes labeled WN2 through WN9 based on the ionization state of the nitrogen and the relative strengths of different emission lines. The lower numbered subtypes, like WN2 through WN5, correspond to hotter surface temperatures and a more highly ionized nitrogen. The higher numbered subtypes, like WN7 through WN9, correspond to cooler surface temperatures and less highly ionized nitrogen. The temperature range across the WN sequence is enormous. WN2 stars can have effective surface temperatures of 150,000 Kelvin or more. WN9 stars might be down around 30,000 Kelvin. Both are still much hotter than an ordinary sun-like star, but the range across the WN family reflects the diversity of physical conditions in stars at different stages of the stripping process. There is another distinction within the WN class that turns out to matter. Some WN stars still show hydrogen lines in their spectra alongside the strong nitrogen lines. These are stars whose outer envelope is mostly gone, but not entirely gone. They are still in transition. The wind is still working through the last remnants of the hydrogen skin. Astronomers give these an extra label. They are called WN with hydrogen, or sometimes given the designation WNH. Then there are WN stars whose spectra show essentially no hydrogen at all, just nitrogen and helium. These are stars whose hydrogen envelopes have been completely removed. Nothing but the CNO processed material and helium is left to shine. These are the pure nitrogen sequence Wolf-Rayet stars. But the story does not end with nitrogen. If a Wolf-Rayet star continues to lose mass, if the wind keeps eating through layer after layer, eventually the wind will chew past the CNO processing zone entirely. Below that zone, in the deep interior of the star, is a region where a different kind of nuclear fusion has been happening. This is helium burning. In the core of a massive star that has exhausted its central hydrogen, the core contracts and heats until helium fusion ignites. Helium fusion proceeds through what is called the triple alpha process, in which 3 helium-4 nuclei come together to form one carbon-12 nucleus, releasing energy. Some of that carbon is then hit by another helium nucleus and gets fused further into oxygen-16. The net result of helium burning is a core that is enriched in carbon and oxygen and depleted in helium, relative to what it was when helium burning began. If the wind of a Wolf-Rayet star strips away not just the outer envelope, but also the entire CNO processing zone above the core, then what is exposed at the surface is helium-burning material, enriched in carbon, enriched in oxygen. The nitrogen that was so obvious in the WN spectrum is gone, because the nitrogen was in the CNO layer, which has been peeled away. What you see instead is carbon. Strong carbon emission lines. Emission lines of highly ionized carbon and highly ionized oxygen. This is the spectrum of a Wolf-Rayet star of the carbon sequence. It is called a WC star, and it is the signature of a Wolf-Rayet star whose wind has cut all the way through the hydrogen envelope, all the way through the CNO processing layer, and is now exposing the products of helium fusion itself. Think about what this means for a moment. A WC star is a star whose surface, the outermost visible layer of material, is essentially made of the ashes of helium burning, carbon and oxygen. In terms of chemistry, you're looking at something that would, in an ordinary star, be buried deep inside, kilometers below the surface, hidden under enormous overlying layers of unprocessed material. In a WC star, all of that hiding material is gone, blown away. The surface is the core. The WC class also has subtypes, labeled WC4 through WC9, based on ionization state and the ratio of carbon lines to oxygen lines. The distinction between WC subtypes is a matter of exactly which stage of helium burning is being exposed. In the earlier stages of helium burning, the ratio of carbon to oxygen in the core is high because oxygen has not had much time to form yet. In the later stages, the ratio shifts toward oxygen because more of the carbon has been converted onward. So, a Wolf-Rayet star that has recently started exposing helium-burning material will show a WC spectrum with strong carbon and weaker oxygen lines. A star that has been exposing helium-burning material for a longer time, and whose surface reflects a more advanced stage of core evolution, will show relatively stronger oxygen lines. And there is a further stage. Some very rare Wolf-Rayet stars show spectra dominated not by carbon, but by oxygen. Extraordinarily strong emission lines of highly ionized oxygen. sometimes with silicon and other heavier elements starting to appear. These are called WO stars, the oxygen sequence Wolf-Rayet stars. WO stars are exceedingly rare. Only a handful are known in the entire local universe. They represent the deepest excavation that a Wolf-Rayet wind has managed to achieve. The surface of a WO star is essentially the residue of very advanced helium burning, or possibly the beginning stages of carbon burning. These are stars whose wind has stripped them so severely that what is left is closer to the final fusion shell than to the original main sequence configuration. They are the endpoint of the stripping process, or nearly so. So the WN, WC, and WO classification is not just a set of labels. It is a chronology, a physical sequence that traces how deep the wind has eaten into the star. WN stars are those whose wind has removed the hydrogen envelope, but not yet reached below the CNO layer. WC stars are those whose wind has continued further and exposed helium-burning material. WO stars are those whose wind has stripped essentially everything and revealed material near the final stages of nuclear processing. Each classification is a signature of a different depth of erosion. When astronomers see a WN2 star, they know the surface is at one specific chemical layer of what used to be a massive stellar interior. When they see a WC6 star, they know the surface is at a different, deeper layer. The classification system is a map of the star's interior, made visible from the outside because the wind has done the excavating for us. There is one more piece of the picture that makes all of this even more dramatic. The exposed surface of a Wolf-Rayet star is not just chemically strange, it is also physically strange. The temperatures are extreme. The effective surface temperature of a hot WN star can reach 150,000 Kelvin, which is 30 times hotter than the sun's photosphere. The temperatures at the base of the wind, deep in what would be the interior of a normal star, can approach 200,000 Kelvin. These are temperatures that would, in any other context, be found only in the interior of stars, thousands of kilometers below the surface. In a Wolf-Rayet star, they are found at the outside. The wind has stripped away not just chemistry, but the entire structure that would normally cool the outer layers down to the moderate temperatures characteristic of a photosphere. You are looking at a star whose outside is at the temperature of what should be an inside. This is why Wolf-Rayet stars emit so much of their light in the ultraviolet. The wavelength at which a hot body emits most of its radiation depends on its temperature. The sun, at 5800 Kelvin, emits most of its light in the visible band. A Wolf-Rayet star, at 100,000 Kelvin or more, emits most of its light in the far ultraviolet. Only a fraction of a Wolf-Rayet star's total luminosity ever appears as visible light. Most of it is invisible to our eyes, streaming out at wavelengths that are absorbed by Earth's atmosphere before they can reach the ground. To see a Wolf-Rayet star as it truly appears, you have to observe it from space with an ultraviolet telescope above the atmospheric barrier that filters out most of its actual output. If you could stand near a Wolf-Rayet star and look at it directly, not that you could survive doing so, you would see a small, extremely blue-white, blindingly bright point. Not a large disk like the sun, but a compact object radiating with enormous intensity. Around it, if you had eyes sensitive to the right wavelengths, you would see the wind itself, a translucent, glowing envelope extending outward, its glow coming from the ionization and fluorescence of the metals being pushed out by the star's radiation. You would not see an atmosphere in the sense of a well-defined photosphere with edges. You would see a star whose outer layer is continuously in motion, streaming outward, glowing as it goes, blending into the shell of previously ejected material that surrounds the whole system. And the whole thing would be small. A Wolf-Rayet star is compact by the standards of what a massive star can be. Its progenitor at the beginning of its life may have been a supergiant with a radius of tens or hundreds of times the radius of the Sun. But by the time the wind has done its work and stripped the envelope, the surviving star has contracted down to something more modest, typically only a few dozen solar radii. What you are seeing when you look at a Wolf-Rayet star is essentially the naked exposed core, plus a very thin wind-driving layer above it. All of the extended envelope that used to swaddle the fusion factory is gone. What is left is compact, hot, brilliant, and headed rapidly toward its end. How rapidly is worth stating carefully. A star with an initial mass of 40 solar masses might spend a few million years on the main sequence, fusing hydrogen in its core. It might then spend several 100,000 years as a blue or red supergiant, evolving off the main sequence and beginning to lose mass in earnest. But the Wolf-Rayet phase itself, the period during which the star's surface actually shows Wolf-Rayet characteristics, only lasts a few 100,000 years. In some cases, it may be as short as 100,000 years. In others, perhaps 400,000 or 500,000 years. Compared to the 10 million years the star spent on the main sequence, this is a blink. This is why Wolf-Rayet stars are so rare in the galaxy. It is not just that their progenitors are rare, though that is part of it. It is that even for stars that will become Wolf-Rayet, only a small fraction of their total lifetime is spent in the Wolf-Rayet phase. If you did a census of massive stars at any given moment, the vast majority would be in an earlier stage. Main sequence O stars, blue supergiants, red supergiants, luminous blue variables. Only the small handful that have already stripped themselves down to the point of exposing their interior chemistry will show up as Wolf-Rayet stars. It is like trying to photograph fireworks. The bright, dramatic phase of the shell peaking at its brightest is fleeting, and most of the time when you point your camera at the sky, you are catching an earlier or later moment. The extreme mass loss that a Wolf-Rayet star sustains during its brief lifetime has consequences beyond the star itself. It changes the local interstellar medium. It reshapes the region of space around the star. The winds carve out enormous cavities in the surrounding gas, called wind-blown bubbles, that can extend for tens of light years. Inside these cavities, the density of gas is much lower than in the surrounding interstellar medium because the wind has swept everything outward. The walls of the bubbles are dense shells of compressed gas, glowing from the shocks generated as the wind slams into slower moving material. These bubbles are not just interesting features. They can trigger new star formation in the dense, compressed shells at their boundaries. A Wolf-Rayet star, before it explodes as a supernova, may already have shaped its neighborhood into a form that will, generations later, give rise to new stars. And the chemistry the wind ejects is important too. When a Wolf-Rayet star blows off its envelope, it is not just returning hydrogen to the interstellar medium. During the WN phase, it is enriching the surrounding gas with nitrogen. During the WC phase, it is enriching it with carbon. Over the course of the Wolf-Rayet lifetime of a single star, that star can inject enough carbon and nitrogen into its neighborhood to significantly alter the composition of the local gas. When new stars form from that gas, they inherit the chemistry the Wolf-Rayet star left behind. The next generation of stars, and the planets that form around them, are made partly out of material that was cooked in the core of a massive star and then blown into space by a violent wind. In this sense, Wolf-Rayet stars are among the most important sources of certain elements in the universe. They are chemical engines that take primordial hydrogen and helium and turn it into the more complex material that everything else, including us, is eventually made of. So when you look at a Wolf-Rayet star and see its spectrum, what you are actually reading is a document about the star's insides. The strong emission lines are not just aesthetic curiosities. They are the star telling you, in the language of atomic physics, exactly what layer of its original interior is currently exposed at its surface. Nitrogen means CNO cycle ashes, carbon means helium burning residue, oxygen means something even deeper. And once you understand this language, the sky opens up in a new way. The population of Wolf-Rayet stars in our galaxy and in other galaxies is not just a random set of hot bright objects. It's a distribution of stars caught at various depths of the stripping process. And the statistics of that distribution tell you about the physics of massive star evolution, about how long each phase lasts, about how different environments affect the mass loss, and about what these stars are ultimately headed toward. Because they are headed somewhere. That is the last thing to say before we move on. A Wolf-Rayet star is not a stable configuration. The naked core, the wind, the whole peculiar arrangement of a hot compact fusion factory blowing itself apart cannot last forever. The star has already used up most of its nuclear fuel by the time it reaches this stage. What remains is a countdown. The core continues to contract and heat. It moves through the successive stages of nuclear burning at increasing speed. Carbon burning, neon burning, oxygen burning, silicon burning, each stage lasting a fraction of the time of the one before it. By the time the star reaches the final phases, when the core is fusing silicon into iron, the remaining lifetime is measured not in millennia, but in days. And when the core finally runs out of nuclear fuel that can release energy through fusion, when the ability to hold itself up against gravity fails, the entire structure collapses. What happens next depends on how much mass the star has left, on how much angular momentum it has, on the details of the collapse. In some cases, the outcome is a spectacular explosion. In others, the outcome is silent, and the star simply disappears behind an event horizon. In every case, the peculiar structure that a Wolf-Rayet star represents, the exposed core plus the wind, plays a crucial role in determining what comes next. Because a star that has already stripped itself down to its inner layers is not going to die the way a star with an intact envelope would die. It is going to die differently. And the difference between those deaths is written in the surface chemistry, in the mass loss history, in the structure that the wind has left behind. Everything a Wolf-Rayet star does during its brief, luminous life sets the stage for what will happen at the end. And the ending is going to be extraordinary. There is a specific moment in the life of a Wolf-Rayet star when everything changes. It happens deep inside the star, in the core, in a region so far below the visible surface that no light from that place will ever reach us directly. The core has spent the last few 100,000 years contracting and heating. It has burned through helium, it has burned through carbon, it has burned through neon and oxygen. Each stage has been faster than the last, because at each stage the amount of energy released per fusion reaction has been smaller, and the core has had to work harder to hold itself up. By the time the star reaches silicon burning, the final stage, the whole process has accelerated to a manic pace. Silicon burning in the core of a massive star lasts not for millions of years, not for centuries, but for about 1 day, give or take, and at the end of that day, the core has produced iron. Iron is where the fusion story ends. Every element lighter than iron releases energy when it fuses into something heavier. Iron does not. Fusing iron into something heavier absorbs energy rather than releasing it, which means the moment the core is made mostly of iron, the star has run out of ways to hold itself up. The energy generation that has been supporting the outer layers against gravity for millions of years suddenly stops. The core, which is now roughly the mass of the Sun packed into a volume smaller than the Earth, cannot resist its own weight anymore. In the space of a fraction of a second, it collapses. What happens next depends on the specifics. If the collapsing core is not too massive, it will crash inward until its density reaches the point where neutrons themselves cannot be squeezed any closer together. At that moment, the collapse stops. The infalling material bounces off the newly formed neutron core, sending a shockwave hurtling outward. The shockwave, boosted by an enormous flux of neutrinos escaping the core, tears through the overlying layers of the star and blows them off into space. This is a supernova. What remains at the center is a neutron star, a compact object about 20 kilometers across, containing more mass than the Sun, spinning rapidly, sometimes shining as a pulsar. If the collapsing core is more massive, the story is different. The bounce may fail. The infalling material may accumulate on the neutron core faster than the shockwave can push it away, and the growing central object may cross a critical mass threshold beyond which no known form of matter can support it. At that point, the collapse continues past neutron density and forms a black hole. In some scenarios, this happens quietly. The outer layers of the star fall into the newly formed black hole, with essentially no fanfare visible from outside. The star simply disappears, and where a brilliant point of light used to be there is now nothing. In other scenarios, part of the outer material still gets blown off in an explosion, but a black hole forms at the center rather than a neutron star. The details of which star goes which way are still not entirely settled. The physics of core collapse is genuinely complicated, involving the intricate balance between infalling matter, neutrino luminosity, shock revival, and dozens of other effects that only supercomputers can properly simulate. But there is one clean generalization that is well established. If a star has managed to shed its outer hydrogen envelope before it collapses, the appearance of its supernova will be different from that of a star that still had its envelope. And a Wolf-Rayet star, by definition, has already thrown its envelope away. This is where the whole story finally connects. The stripping that has been going on for hundreds of thousands of years, all that violent radiation-driven mass loss, all that outward flow of material at thousands of kilometers per second, has been setting up a very specific stage. When the star finally reaches the moment of core collapse, it is not a normal massive star. It is a naked core with essentially no hydrogen envelope. In many cases, it does not even have a helium envelope, and the supernova that results from the collapse of such a star does not look like an ordinary supernova. It looks like something distinctive. Astronomers had noticed for decades that supernovae come in different types. The initial classification, worked out in the middle of the 20th century, was based on what the spectrum of the exploding star looked like in the days and weeks after the explosion. Type 1 supernovae showed no hydrogen lines in their spectra. Type 2 supernovae did show hydrogen lines. This basic split turned out to be tracking a real physical distinction. Type 2 supernovae came from stars that still had substantial hydrogen envelopes at the moment of explosion. Type 1 supernovae came from stars whose envelopes were, for one reason or another, gone. Within Type 1, astronomers eventually recognized subcategories. Type 1. A supernovae, the classic thermonuclear explosions of white dwarfs, were spectroscopically distinct and physically completely different from the others. But there was a second family of hydrogen-free supernovae, and these were coming not from white dwarfs, but from massive stars whose envelopes had been stripped away. These were the ones that turned out to be the endpoints of stripped envelope evolution. Depending on exactly what had been stripped, they were divided further. Type 1b supernovae showed helium in their spectra, but no hydrogen. Type 1c supernovae showed neither hydrogen nor helium. The physical picture that emerged from this classification is beautifully simple. A Type 1b supernova comes from a star that had lost its hydrogen envelope, but still had a helium layer at the time of core collapse. When that star explodes, the helium layer gets blown off along with everything else, and its signature shows up in the supernova spectrum. A Type 1c supernova comes from a star that had lost not only its hydrogen envelope, but also its helium envelope. When that star explodes, there is essentially no hydrogen and essentially no helium in the ejector, because those layers were blown away by the wind long before the explosion happened. Now match this to the Wolf-Rayet classification, and the connection becomes obvious. A WN star has stripped away its hydrogen, but still has a helium-rich outer layer. When a WN star reaches core collapse and explodes, the result should look like a Type 1b supernova. A WC or WO star has stripped away not only the hydrogen, but also the helium. When a WC or WO star reaches core collapse, the result should look like a Type 1c supernova. The spectral chemistry of the Wolf-Rayet star translates directly into the spectral chemistry of the supernova that terminates it. The archaeological signatures on the surface of the living star become the fingerprints in the debris of the dead one. This link has been strongly supported by rate arguments, environmental studies, and modelling, though direct progenitor identification has been genuinely hard. When a supernova goes off in a distant galaxy, astronomers can go back and look at archival images of the site to try to find the star that just exploded. For most Type 2 supernovae, this technique has been very successful. Red supergiants, the progenitors of the most common Type 2 events, are luminous and cool and easy to spot in optical images taken years before the explosion. For Type 1b and 1c supernovae, the technique has been much harder. Wolf-Rayet stars are compact and hot, and although they are extremely luminous, most of that luminosity is emitted in the ultraviolet. In optical images taken by ground-based telescopes, they are less obvious than a red supergiant of comparable mass. Only a small number of stripped envelope supernovae have had their progenitors clearly identified in pre-explosion images. The evidence connecting Wolf-Rayet stars to Type 1b and Type 1c supernovae is therefore mostly indirect. It comes from the rates at which these events occur, from the types of environments in which they preferentially happen, from the properties of the ejector as measured after the explosion, and from theoretical models of stellar evolution. Taken together, These lines of evidence make the connection very strong. But it is worth being honest that the individual case, star by star, has been elusive to prove. Whatever exactly explodes and however cleanly the connection is made, the endpoint of a Wolf-Rayet star's life is more than just a supernova. The really striking possibility is what may sit at the center after the explosion is over. Because a stripped Wolf-Rayet star with a substantial remaining mass at the moment of core collapse is one of the best candidates in the universe for producing a black hole. Here's the reasoning. The mass of the compact object that forms after a core collapse depends primarily on the mass of the core at the moment of collapse, and on how much of the overlying material either gets blown off or falls back onto the central object. A star that started life with, say, 40 solar masses and has, through its Wolf-Rayet wind, lost 20 solar masses of hydrogen envelope before core collapse, still has 20 solar masses of material near the core. Some of that will go into the supernova ejector. Some of it may fall back and be added to the central compact object. If enough falls back, the central object exceeds the maximum mass a neutron star can have, which is somewhere around 2 to 3 solar masses, depending on the details of the neutron star equation of state. And it collapses further into a black hole. Whether that happens depends on many things. The initial mass matters, the metallicity matters because low metallicity stars have weaker winds and retain more mass, ending up with more massive cores at collapse. The rotation rate matters. The presence of a binary companion matters. Sometimes very much. There are massive stars that end up producing neutron stars, and there are massive stars that end up producing black holes, and the boundary between them is not a sharp line. It is a probabilistic region where various factors combine to determine the outcome. But statistically, Wolf-Rayet stars, especially those that started with high initial masses and are found in relatively low metallicity environments, are prime candidates for black hole formation. When astronomers list the most likely progenitors of stellar mass black holes in the modern universe, Wolf-Rayet stars are always near the top of the list. There is a specific caveat here that deserves emphasis. It is tempting to say something clean like, this WC star will collapse into a black hole, and the WN star will produce a neutron star. But the truth is that the field does not yet have that level of confidence. Which specific stars end up as which kind of remnant is still an active area of research, and the answers depend sensitively on things we do not measure directly. The rotation of the core at collapse, the exact composition profile, the efficiency of the supernova mechanism itself. What we can say confidently is that Wolf-Rayet stars, as a population, are strongly implicated in the production of stellar mass black holes. What we cannot yet say confidently is which individual Wolf-Rayet star, right now, is destined to leave a black hole behind, versus which is destined to leave a neutron star, versus which is destined to leave essentially nothing at all if the collapse simply swallows the entire star with no explosion. The population level connection is robust. The individual case is not. There is one specific class of stellar deaths in which Wolf-Rayet progenitors are especially prominent, and this class deserves its own moment in the story. These are the long-duration gamma-ray bursts. Gamma-ray bursts were discovered in the late 1960s, initially by military satellites looking for evidence of nuclear tests on the ground. Instead of finding illicit human explosions, the satellites detected bursts of gamma rays coming from random directions in the sky, lasting anywhere from milliseconds to minutes. It took decades to figure out where these bursts were coming from and what was producing them. The eventual answer, developed through the 1990s and 2000s, was that gamma ray bursts come in two broad families: short duration bursts, lasting less than about 2 seconds, are produced by the mergers of two compact objects, usually two neutron stars. Long duration bursts, lasting longer than 2 seconds and sometimes as long as several minutes, are produced by a very specific and very rare kind of stellar death. This specific kind of stellar death that produces a long duration gamma ray burst is called a collapsar. The word was coined to describe a stellar collapse that produces not a normal spherical explosion, but a highly focused, jet-driven outflow. In a collapsar, a rapidly rotating massive core collapses to form a black hole. The material falling toward the black hole cannot all go straight in because it is rotating too fast. Instead, it forms an accretion disk around the newly formed black hole. Magnetic fields in the disk, powered by the extreme conditions near the black hole, launch narrow relativistic jets outward along the rotation axis. If those jets manage to punch through the outer layers of the collapsing star and break out into space, they produce a beam of gamma rays that we see, if we happen to be in the line of fire, as a long-duration gamma ray burst. For the collapsar mechanism to work, the progenitor star has to satisfy some very specific conditions. It has to have a massive core, one that will produce a black hole rather than a neutron star. It has to be rotating rapidly enough at the time of collapse to produce a well-organized accretion disk. And, crucially, it has to be free of an extended hydrogen envelope. Because if the star still has its hydrogen envelope, the relativistic jets emerging from the central engine will lose their energy plowing through the envelope and never escape into space. Only a stripped star can launch a successful collapsar jet. The mechanics of jet breakout are worth pausing on because they are extraordinary. Consider the situation just after the black hole forms. Those newly launched jets are extremely narrow, opening at angles of only a few degrees, and they carry an enormous amount of energy concentrated into that narrow cone. But they have to travel outward through what is left of the star before they can escape into space. Even for a stripped Wolf-Rayet progenitor, that means punching through several solar masses of dense stellar material, stretching from the central engine out to what used to be the wind driving layer. The jet does this by ramming through the star at speeds approaching the speed of light, drilling a cavity in the material as it goes. If the star has been sufficiently stripped, the drilling takes only a few seconds. If any hydrogen envelope is still present, the drilling can take too long, the jet loses coherence and no gamma ray burst is produced. The margin is narrow. A star that has almost stripped itself down to the collapsar configuration, but not quite, will collapse silently. A star that has completed the stripping process will produce one of the brightest events in the universe. The Wolf-Rayet phase is what makes the difference. There is one supernova in the historical record that has become the canonical example of this connection. In April of 1998, a satellite in orbit detected a burst of gamma rays from the direction of a small galaxy in the southern constellation Telescopium. The burst itself was unremarkable by gamma ray burst standards, relatively weak compared to the more distant ones astronomers were used to seeing, but its position was well determined. Within days, optical astronomers pointing telescopes at the location noticed something extraordinary. A supernova had appeared in the same galaxy, in the same direction as the burst, at the same time. The supernova was catalogued as SN1998 BW. This was the first time in history that a specific gamma-ray burst had been unambiguously associated with a specific stellar explosion. When astronomers took the spectrum of the supernova, they found something striking. It was a Type 1c event. No hydrogen, no helium. Exactly the signature expected from the death of a star that had been stripped of both its hydrogen and helium envelopes. In other words, exactly the signature expected from the death of a WC or WO Wolf-Rayet star. And the supernova was unusually energetic, with ejecta moving so fast that its spectral lines were broadened far beyond what a normal Type 1c event would show. The astronomers coined a new term for it. They called it a hypernova, a supernova of extraordinary power, and they realized they were looking at the visible signature of the same collapsar event that had produced the gamma-ray burst. One star, one collapse, two observable phenomena arriving simultaneously because both were coming from the same catastrophe. The galaxy hosting the event was a small, low luminosity spiral, the kind of environment where metallicity tends to be lower than in a massive galaxy like our own. That was a good fit with the theoretical picture. Low metallicity Wolf-Rayet progenitors retain more of their mass because their winds are weaker, and low metallicity environments have turned out to be strongly preferred hosts for long-duration gamma-ray bursts across the population. In the decades since, several more gamma-ray burst supernova pairs have been identified, and every one of them has followed the same pattern. The supernova is always a broadline Type 1c. The progenitor is always inferred to be a stripped massive star, consistent with a Wolf-Rayet origin. The theoretical prediction and the observational reality have converged on the same picture. Long-duration gamma-ray bursts come from the collapse of stripped massive stars, and the stars that were doing the stripping are the Wolf-Rayet stars we can see right now in our own galaxy and its neighbors. Not every Wolf-Rayet star will produce a long-duration gamma-ray burst. Most will not, because the rotation and mass conditions required are strict. But the population of Wolf-Rayet stars is essentially the population of stars in which the collapsar mechanism could work at all. The stellar death that produces some of the most energetic phenomena in the universe is essentially the Wolf-Rayet endpoint under the right rotational conditions. This means that Wolf-Rayet stars, as a class, are the ancestors of some of the most extreme events the universe ever produces. Long-duration gamma-ray bursts are the most luminous single events observed in the universe. For a few seconds, one of these bursts outshines everything else in the sky combined. They can be seen from clear across the observable universe. Some of the most distant objects known are the afterglows of long-duration gamma-ray bursts. When we look at those bursts, we are looking at the deaths of specific massive stars, and those stars are almost certainly stripped envelope stars of the general kind that Wolf-Rayet stars represent. Every burst is a signature of one of these deaths, magnified by focusing effects and by the extreme physics of a newly formed black hole into a beacon that can reach us from the earliest epochs of cosmic history. There is another line of evidence that has recently come into play. Ever since the first direct detection of gravitational waves in 2015, astronomers have been watching a new kind of sky. The gravitational wave detectors of LIGO and Virgo detect ripples in space-time, and by far the most common events they see are mergers of pairs of black holes. In the decade or so since detection began, well over 100 of these black hole mergers have been observed, and the masses of the black holes involved have turned out to be surprising. The black holes in these mergers are typically in the range of 10 to 50 solar masses, occasionally more. That is a substantial size for a stellar mass black hole. It is bigger than what most astronomers before the gravitational wave era would have predicted for the typical remnant of a massive star. It has forced a reconsideration of how black holes form and how they end up in binaries. And one of the key conclusions has been that whatever produced these black holes must have been a stripped, massive star. Because to end up with a compact object of 10 or 20 or 30 solar masses, you need a star that reached core collapse while still carrying that much mass. A star that had lost most of its envelope but retained a massive core. In other words, a Wolf-Rayet star, or something very similar to it. The story goes deeper still, because the fact that these are binary black holes matters. To form a merging black hole binary, you need two massive stars that either were born as a close pair and evolved together, or that ended up gravitationally bound to each other in some other way. In the standard picture of isolated binary evolution, two massive stars orbit each other closely, and each of them eventually reaches core collapse. If both of them produce black holes, and if the binary survives the two supernova kicks that could unbind it, you end up with two black holes in orbit. Those black holes will slowly spiral inward as they radiate gravitational waves, and eventually they will merge. That merger is what LIGO detects. For this picture to work, both stars in the binary need to have gone through a stripped envelope phase before their black holes formed. And Wolf-Rayet stars, as the archetype of stripped massive stars, are natural candidates for both members of these progenitor pairs. Not the only candidates. There are other channels through which massive black hole binaries can form, including dynamical channels in dense star clusters and channels involving chemically homogeneous evolution. But even in the alternative channels, the individual stars involved often go through Wolf-Rayet-like phases before they collapse. Wolf-Rayet stars, or their close analogues, are woven through the story of gravitational wave sources. There is one more twist worth mentioning. Even the mergers themselves may sometimes involve peculiar progenitor histories. Some of the black holes detected by LIGO are unexpectedly massive by the standards of what stellar evolution was predicted to produce. And these observations are pushing theorists to rethink the details of how mass loss and stripping affect the final black hole masses. The dependence on metallicity is a major factor. In the low metallicity conditions of the early universe, or in low metallicity dwarf galaxies today, massive stars retain more of their initial mass because their winds are weaker. That should produce more massive final black holes. The population of gravitational wave sources therefore carries information about how stellar mass loss changes with metallicity across cosmic time. And Wolf-Rayet stars are again central to interpreting what we see. Putting all of this together, the endpoint of a Wolf-Rayet star turns out to be one of the most consequential events in the universe. A stripped envelope supernova in most cases. A neutron star, or more likely for the most massive progenitors, a black hole. A long-duration gamma ray burst, in the special cases where the rotation is right. A future gravitational wave source if a binary partner is nearby to make the eventual merger possible. Wolf-Rayet stars are not just interesting objects in their own right. They are the ancestors of some of the most extreme phenomena the cosmos produces. Consider what this means. When you look at a Wolf-Rayet star, you are looking at a star that is roughly 100,000 years away from a spectacular death, give or take a bit. You are looking at a star whose wind has been setting the stage for that death for hundreds of thousands of years. You are looking at a star that is a leading candidate to leave a black hole behind. You are looking at a star that, if the rotational conditions cooperate, could produce a burst of gamma rays that will outshine every other object in the observable universe for a few seconds. You are looking at a star whose eventual black hole may, in the very distant future, spiral inward toward another black hole and merge, producing ripples in space-time that will still be detectable, in principle, by any civilization that happens to have gravitational wave detectors when those ripples finally pass through. The chain of events is long and it stretches deep into the future. A Wolf-Rayet star that is shining right now, in some corner of the Milky Way or in one of the nearby galaxies, is a link in a chain that begins with the formation of a very massive star from a collapsing cloud of gas and dust, proceeds through millions of years of hydrogen fusion, transitions through a stripping phase driven by radiation and winds, arrives at the exposed core state we call Wolf-Rayet, ends in core collapse and a compact remnant, and potentially culminates hundreds of millions of years later in a merger with another compact object that sends gravitational waves out into the cosmos. The Wolf-Rayet stage is just one specific episode in this saga, but it is a decisive one. It is the episode that determines how much mass the star has when it dies, what kind of remnant it leaves behind, and what kind of death it experiences on the way out. There is a final observation that ties this all together. The stripping that a Wolf-Rayet star does is what makes many of these extreme outcomes possible. A star that keeps its envelope until the moment of collapse ends up producing a Type II supernova, most likely leaving behind a neutron star, most likely not producing any exotic beamed radiation. It has a comparatively mundane death, at least by the standards of what the universe can produce. A star that strips itself, on the other hand, opens up options. It can produce a Type 1b or Type 1c supernova. It can leave behind a black hole in the mass range LIGO can detect. It can, in the right conditions, drive a collapsor jet and produce a gamma ray burst. The self-stripping process, the years upon years of wind driving away layers of the star, is what qualifies the star for these more extreme endings. Without the stripping, you get a quieter death. With the stripping, you get access to the most violent phenomena the cosmos allows. And that is what a Wolf-Rayet star ultimately is. It is a star that has traded stability for possibility. It has given up the safety of its envelope and turned itself into a naked, fragile, hot core. It has spent hundreds of thousands of years dismantling itself for reasons that come down to the fundamental physics of how radiation interacts with matter in extreme conditions. And in doing so, it has prepared itself for a death that will be, one way or another, one of the most consequential moments in the neighborhood of its host galaxy. A stripped envelope supernova, a black hole, perhaps a gamma ray burst, perhaps the ancestor of a future gravitational wave source. The Wolf-Rayet stage is the pivot on which all of this turns. When the final collapse comes, the star will not have time to notice. The core will simply run out of fuel and give way to gravity. The neutrinos will pour out. Some fraction of the outer material will be blown into space. Some fraction may fall back onto the newly formed compact object. If everything conspires the right way, a jet will form and punch outward through what remains of the star, sending a beam of gamma rays into the universe. If a companion is nearby, a new binary compact object will be created. And in the silence that follows, there will be either a rapidly spinning neutron star, or an event horizon, or nothing visible at all. Whatever specifically is left behind, the story that began with a very massive star and went through the WN and WC and WO stages and ended in silent gravity will be complete. The universe will have used one of its rarest and most extreme kinds of objects to add one more remnant to its slowly growing collection. And somewhere in that collection, in some binary system perhaps hundreds of light years across, two of those remnants will be slowly spiraling toward each other, waiting for their own moment. And when that moment comes, they will send a signal that will travel across space for perhaps 1 billion years, and eventually reach some observer somewhere with the right instruments, and remind that observer that the universe long ago made a Wolf-Rayet star, and stripped it bare, and turned it into a black hole, and set in motion a chain of events whose echo they are only now feeling.